according to the definitions provided in Article 100 of the National Electrical Code, often abbreviated as NEC, a rooftop unit can indeed be classified as an appliance. This is because it falls under the category of utilization equipment, which is generally not considered industrial, and is manufactured in standardized sizes or types. It is installed or connected as a unit to perform a specific function, in this case, air conditioning. Because the rooftop unit is classified as an appliance, it becomes an integral part of a branch circuit. The NEC defines a branch circuit as a circuit that supplies electrical energy to one or more outlets intended for connection to appliances. Therefore, the rooftop unit, being an appliance, must be connected to a branch circuit to receive its power supply. Importantly, the NEC does not have a blanket requirement mandating that all branch circuits serving appliances must be installed using electrical metallic tubing, abbreviated as EMT, conduit. Consequently, the use of metal-clad cable, often called MC cable, is generally permissible for such applications. However, the preference expressed by the engineer for EMT conduit likely stems from specific considerations related to the project. These considerations might include enhanced protection against environmental factors such as moisture or UV radiation, or a greater degree of physical protection against potential damage. While MC cable offers a degree of protection, EMT conduit may be deemed more robust in certain environments or applications. To provide a more detailed understanding of the considerations involved, let's explore some relevant aspects of electrical codes and wiring practices. Firstly, the National Electrical Code, NEC, serves as the primary standard for electrical installations in the United States. It outlines the minimum requirements for safe electrical design, installation, and inspection. Secondly, Article 100 of the NEC provides definitions for various terms used throughout the code. These definitions are crucial for proper interpretation and application of the code requirements. Thirdly, branch circuits are the circuits that extend from the final overcurrent protection device, such as a circuit breaker or fuse, to the outlets or equipment they supply. They are categorized based on their ampacity, which is the maximum current they can carry safely, and the type of loads they serve. Fourthly, EMT conduit is a type of rigid metal conduit commonly used for electrical wiring. It provides excellent physical protection for conductors and can be used in various environments, including those that are wet or corrosive. Fifthly, MC cable is a factory-assembled cable consisting of insulated conductors enclosed in a metallic sheath. It offers a convenient and relatively easy to install wiring method, but it may not provide the same level of physical protection as EMT conduit in certain situations. Now, let's consider the specific factors that might influence the choice between EMT conduit and MC cable for a rooftop unit branch circuit. Environmental conditions are a key consideration. If the rooftop unit is located in an area exposed to harsh weather, such as direct sunlight, rain, snow, or extreme temperatures, EMT conduit may be preferred. The metallic sheath of MC cable can degrade over time when exposed to prolonged UV radiation or moisture. EMT conduit, especially when properly installed with watertight fittings, offers superior protection against these elements. Physical protection is another important factor. If the rooftop unit is located in an area where it is susceptible to physical damage, such as from falling objects or vandalism, EMT conduit may be the better choice. EMT conduit is more resistant to impact and crushing than MC cable. Cost is often a consideration, but it should not be the sole determining factor. MC cable is generally less expensive to purchase and install than EMT conduits. However, the long-term cost of repairs or replacements due to damage or degradation may outweigh the initial cost savings. Installation requirements can also play a role. MC cable is generally easier and faster to install than EMT conduit, particularly in tight spaces or where there are many bends or offsets. However, EMT conduit may be required in certain locations by local codes or regulations. The engineer's specifications are crucial. As the engineer has specified EMT conduit, it is important to understand their reasoning. They may have specific concerns about the environment, physical protection, or other factors that led them to this decision. It's also important to consider the specific requirements of the equipment being supplied. Some rooftop units may have specific wiring requirements or recommendations from the manufacturer. These requirements should be followed to ensure proper operation and safety. In summary, while the NEC generally permits the use of MC cable for branch circuits to appliances, there are circumstances where EMT conduit may be a more appropriate choice. These circumstances include harsh environmental conditions, potential for physical damage, and specific requirements of the equipment or the engineer's design. In the context of your project, since the engineer has requested EMT conduit, it is advisable to comply with this request. Doing so ensures that the installation meets the specific requirements of the project and the engineer's design intent. It also helps to avoid potential problems or conflicts later on. It is also important to consider the specific requirements outlined in Article 300.3 of the National Electrical Code, which addresses the requirements for the installation of conductors with other equipment. Article 300.3, subsection B, number 1, states that all conductors of the same circuit, including the neutral and equipment grounding conductor, must be installed in the same raceway cable or enclosure. This requirement ensures that the magnetic fields produced by the conductors cancel each other out, reducing the risk of inductive heating and voltage drop. Failing to comply with this requirement can lead to serious problems such as overheating of conductors, insulation damage, and even fire. Therefore, it is crucial to ensure that all conductors of the branch circuit to the rooftop unit, including the neutral and equipment grounding conductor, are installed together in the same EMT conduit or MC cable. Furthermore, it is important to consider the ampacity of the conductors used for the branch circuits. The ampacity of a conductor is the maximum current it can carry continuously without exceeding its temperature rating. The NEC provides tables that list the ampacity of various types of conductors based on their size, insulation type, and installation method. It is essential to select conductors with an ampacity that is sufficient to carry the load of the rooftop unit plus any additional loads that may be connected to the same branch circuit. The ampacity of the conductors must also be protected by an overcurrent protection device, such as a circuit breaker or fuse, that is sized appropriately for the conductor ampacity. The overcurrent protection device must interrupt the circuit if the current exceeds the conductor ampacity, preventing overheating and potential fire hazards. The NEC provides specific requirements for the sizing of overcurrent protection devices in Article 240. Another important consideration is the grounding of the electrical system. Grounding is the process of connecting the non-current carrying metal parts of electrical equipment to the earth. Grounding provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protection device to trap and clear the fault. Grounding also helps to reduce the risk of electric shock by limiting the voltage on metal parts that could become energized due to a fault. The NEC provides detailed requirements for grounding in Article 250. These requirements cover various aspects of grounding, such as the size and type of grounding conductors, the methods of connecting grounding conductors to equipment, and the grounding electrode system, and the requirements for bonding metal parts together to create a continuous grounding path. In addition to the general grounding requirements, there are also specific requirements for grounding equipment located on rooftops. These requirements are intended to ensure that the equipment is properly grounded and that the grounding system can withstand the effects of lightning strikes. Article 250.106 of the NEC requires that metal equipment located on rooftops be bonded to a grounding electrode system that is separate from the building's grounding electrode system. This separate grounding electrode system is intended to provide a dedicated path for lightning current to flow to ground, minimizing the risk of damage to the building's electrical system. The grounding electrode system for rooftop equipment typically consists of one or more ground rods driven into the earth near the equipment. The ground rods are connected to the equipment using grounding conductors that are sized appropriately for the expected fault current. In addition to grounding, bonding is another important aspect of electrical safety. Bonding is the process of connecting metal parts together to create a continuous electrical path. Bonding helps to reduce the risk of electric shock by ensuring that all metal parts are at the same potential. If a fault occurs, The fault current will flow through the bonding conductors, causing the overcurrent protection device to trip and clear the fault. The NEC provides detailed requirements for bonding in Article 250. These requirements cover various aspects of bonding, such as the size and type of bonding conductors, the methods of connecting bonding conductors to metal parts, and the requirements for bonding different types of metal parts together. In addition to the general bonding requirements, there are also specific requirements for bonding equipment located on rooftops. These requirements are intended to ensure that all metal parts of the equipment are properly bonded together and to the building's grounding system. Article 250.92, subsection B, number 2, of the NEC requires that all metal parts of rooftop equipment be bonded together using bonding jumpers. The bonding jumpers must be sized appropriately for the expected fault current and must be installed in a manner that provides a reliable electrical connection. It is also important to consider the requirements for protecting conductors from physical damage. Conductors that are exposed to physical damage must be protected by conduit, tubing, or other suitable means. The type of protection required depends on the location of the conductors and the type of physical damage to which they are exposed. For example, conductors that are located in areas where they are subject to vehicular traffic must be protected by rigid metal conduit or other heavy-duty protection. Conductors that are located in areas where they are subject to moisture or corrosion must be protected by corrosion-resistant conduit or tubing. The NEC provides detailed requirements for protecting conductors from physical damage in Article 300.4. These requirements cover various aspects of conductor protection, such as the types of protection required for different locations and the methods of installing protective devices. In addition to the NEC requirements, it is also important to consider any local codes or regulations that may apply to the electrical installation. Local codes or regulations may impose additional requirements or restrictions that are not found in the NEC. It is the responsibility of the electrical contractor to be familiar with and comply with all applicable codes and regulations. Furthermore, the selection of wiring methods must also adhere to the guidelines provided in Chapter 3 of the NEC, which covers wiring methods and materials. This chapter details the acceptable uses and restrictions for various wiring methods, including EMT and MC cable. For example, Section 330.10 of the NEC specifies the uses permitted for MC cable, while Section 358.10 outlines the permitted uses for EMT. Understanding these specific requirements is essential for ensuring code compliance and safety. Considering voltage drop is another important aspect of branch circuit design. Voltage drop occurs when the voltage at the load end of a circuit is lower than the voltage at the source end. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To minimize voltage drop, it is important to select conductors with an appropriate size and to keep the circuit length as short as possible. The NEC provides guidance on calculating voltage drop in Chapter 9 Informative Annex C. Furthermore, it is also prudent to consult with the equipment manufacturer specifications for recommended wiring practices. Equipment manufacturers often provide specific instructions regarding conductor sizing, wiring methods, and grounding requirements. Adhering to these recommendations can help ensure the safe and reliable operation of the equipment. In addition to the technical aspects of wiring, it is also important to consider the workmanship of the electrical installation. A properly installed electrical system is more likely to be safe and reliable. The NEC requires that all electrical work be performed in a neat and workmanlike manner. This means that conductors must be properly supported, connections must be tight and secure, and all equipment must be installed according to the manufacturer's instructions. It is also important to inspect the electrical installation carefully to ensure that all work has been performed correctly. Any defects or deficiencies must be corrected before the system is energized. In conclusion, the decision to use EMT conduit or MC cable for a rooftop unit branch circuit depends on a variety of factors, including the environmental conditions, the potential for physical damage, the specific requirements of the equipment, the engineer's design intent, and the applicable codes and regulations. While the NEC generally permits the use of MC cable for branch circuits to appliances, there are circumstances where EMT conduit may be a more appropriate choice. By carefully considering all of these factors, you can ensure that the electrical installation is safe, reliable, and compliant with all applicable requirements.